After the hour. I'm really delighted to welcome Professor Michele Trenti to Toronto. He's joining us all the way from Australia. Michele did his bachelor's and PhD studies at the Scuola Normale Superiore in Pisa, Italy, graduating in 2005. He went on to do postdocs at the Space Telescope Science Institute and at the University of Colorado at Boulder. And then from 2012 to 14, he was a Kavli Institute Fellow at the University of Cambridge. He began his current position at the University of Melbourne in 2014. One of Michele's main research focuses is the formation of the first galaxies in the universe. And he does this both from the modeling and numerical simulation side of things, as well as observationally. And so he's made extensive use of the Hubble telescope and has been one of the top 10 observers, top 10 users of the Hubble telescope since 2001. And he'll be telling us about this work today. In addition to being a user of space telescopes, he's recently become a creator of space telescopes as the PI of the SPIRIT CubeSat, which is an X-ray and gamma ray instrument and is due to launch next year. And we'll hear about SPIRIT as well in this talk. On a more personal note, I met Michele when he was on the faculty of the Vatican Observatory Summer School in 2014. The topic of that school was galaxies near and far, young and old. And I remember being really impressed not only by the quality of his lectures and how he brought his research to life in the classroom, but I was also impressed at what a good mentor he was to the graduate students who were at the school. These were junior graduate students from all over the world, from all 5 continents, and I think he inspired a lot of them early on in their careers. It was soon after that school that he founded the Kathmandu Astrophysics School as a further way of opening a door to astronomy research to students who might not otherwise have that kind of opportunity. So once again, Michele, it's really a pleasure to welcome you here, and we're looking forward to your talk. Please take it away.
Yeah, so thank you very much for the invitation to present my research and for the introduction. It is a great pleasure to be here and have the opportunity to tell you a little bit about my recent research on galaxies at cosmic dawn, primarily seen through space telescopes. Developing and launching a telescope in space is a complex, time-intensive and expensive undertaking. Yet space telescopes have a unique advantage over their ground siblings. And this is beautifully illustrated here in this image of the Hubble Space Telescope at about a $5 billion US mission. Space telescopes are above Earth's atmosphere, and therefore they can collect photons with unparalleled efficiency and with reduced foreground noise. So let's have a brief look at the impact of Earth's atmosphere on astronomical observations. First, if we look across the electromagnetic spectrum from gamma X-rays all the way to radio, we can see here in this viewgram a representation of the atmosphere opacity on the vertical axis as a function of wavelength on the horizontal axis. And we can immediately see how only a limited window at specific wavelengths exists with high transmission, so low opacity, and primarily that is at optical, a little bit in the infrared and at radio wavelengths. A second impact of the atmosphere on our astronomical observations, if we consider in particular optical near infrared, is that the photons have to travel through the turbulent layers of the atmosphere, so that induces a time variable refraction index, which blurs our images. That's called seeing effect. Last but not least, and in particularly severe at the infrared wavelengths that we need to observe the distant galaxies at cosmic dawn, atmosphere glows due to diffuse emission from molecular excitation lines, water, OH, and other molecules, limiting our ability to obtain low noise observations. Here we can see a comparison between ground and space observations. On the left-hand side of the view graph, we have a patch of the sky in the goods field, seen with from the ground, from the top of Mauna Kea with the Subaru telescope, an 8-meter class facility, one of the world's best telescopes. And even if we are in visible light, which is very favorable for ground-based observations, we can see how Hubble from space, a telescope which has a mirror of only 2.4 meters, greatly outperforms Subaru, both in terms of angular resolution as well as sensitivity to capturing lower signal-to-noise features in this set of interacting galaxies. So, given all these advantages, it is not surprising to see that there is increased reliance for astrophysics research in the last few decades on space telescopes across the full electromagnetic spectrum, from high energy emission with the Fermi, Swift, NuSTAR, Chandra facilities, all the way even to radio waves. And in particular, the Spectre-R satellite is on highly elliptical orbit, and it is used for ultra-baselong interferometry, combining its observations with ground-based space telescopes. So when talking about space telescopes, I think Hubble, up to this point, is arguably the most productive and the one with the largest impact across astrophysics. And we are all keenly awaiting, of course, to see the first light from the James Webb Space Telescope. And just to highlight one of the amazing achievements that Hubble has given astronomers across its 30+ years of operations. Here, I focused on the discovery of galaxies at cosmic dawn in the first 500 to 800 million years during the epoch of reionization. And I've taken a very personal image for me. I'm showing a random pointing medium deep image with Hubble from the brightest of reionizing galaxies survey that I led in the past years. And it's a series of large pure parallel programs that totaled just over 1,400 orbits with Hubble, or a couple of months of observing time. This IR color composite, we can see a set of 5 galaxy candidates at redshift 8, about 650 million years after the Big Bang, that are representing a potential early overdensity of galaxies at cosmic noon. We can see how Hubble can detect them, but they are just fuzzy red blobs at the limits of sensitivity. So in the next 40 minutes or so, I will present you a little bit more details on my research on galaxies at cosmic dawn, like the little blobs that I've just shown you. And then I'll provide a brief interpretation of those observations through theoretical numerical modeling to show how really the key driver of star formation at cosmic dawn is the build-up of the cosmic web in dark matter, the halo assembly. And finally, I will conclude with an outlook for the future, both with the recently launched James Webb Space Telescope and with nanosatellite constellations, that is distributed-aperture space telescopes. So my research at cosmic dawn aims to contribute to a fundamental area of modern astrophysics, the cosmic origin problem. Where are we coming from? And specifically, how did the first stars and galaxies transform the universe from a chemically simple, homogeneous plasma at the beginning to the complex universe with galaxies, stars, black holes, planets, and life that we have today. And to narrow down the question a little bit more, one key open question is to understand whether the galaxies that we observe with Hubble 13 or more billion years ago are different from today's objects that we can study at incredibly high resolution. And star formation is driven by multifaceted physics processes. And the conditions back then were quite different. Chemically, the gas out of which stars were formed was less abundant in heavy chemical elements, the metals. We had a lower radiative backgrounds from other stars and black holes, but on the other hand, the cosmic microwave background radiation was setting a higher floor to the cooling temperature of cold gas. So all these aspects might play in a complex way and give us different star formation properties for the early objects compared to today's objects. So what we can do is try to understand as much as possible from current observations, complement it with theory, and plan for next generation facilities. So to discover galaxies at cosmic dawn, a large investment of telescope time is required. Because of the expansion of the universe, photons are redshifted, and therefore very qualitatively, the first galaxies appear as red and faint blobs among thousands of galaxies that are closer to us along the line of sight. Over the course of the last few decades, approximate yet very effective and generally reliable color selection techniques, so-called photometric redshift or Lyman break techniques, have been developed and tested, both against simulations and against spectroscopic confirmation for sources at lower redshift, so that now can be applied at cosmic dawn. And we can use data sets such as the Hubble Ultra Deep Field image shown here. It's a very small patch of the sky observed by Hubble for over 3 weeks to create the deepest ever image of the universe seen at these wavelengths. And we can see here, if we zoom in, a galaxy candidate at about redshift 10, about 500 million years from the Big Bang. Since the last servicing mission and the new installation of Wide Field Camera 3, a high-performance near-infrared camera, large samples of galaxies like the ones we have a glimpse at have been constructed in the first billion years after the Big Bang. And here I'm showing a summary of this galaxy number counting exercise, the galaxy luminosity functions, so number of galaxies per magnitude per volume in megaparsec cube comoving on the vertical axis, as a function of galaxy brightness on the horizontal axis, with bright galaxies on the left and faint galaxies on the right. And you can see here the observations with Hubble, with a Lyman break selection of sources, going from 1.5 billion years after the Big Bang, redshift 4, in blue points and fitted Schechter luminosity function lines, all the way to redshift 10, shown in magenta, about 500 million years after the Big Bang. And we can see how we can count galaxies well. There is a clear evolution. It's a log scale on the vertical axis. So we have a rapid buildup of galaxies in about 1 billion year, redshift 10, redshift 4. And the shape of the luminosity function, at least from redshift 4 to redshift 8, is well described by a Schechter luminosity function, so power low at the faint end, exponential drop-off at the bright end, very much like galaxies at lower redshifts. These results have been possible thanks to a combination of multiple surveys with Hubble that can be broadly classified as large area surveys to capture the rare galaxies at the bright end of the luminosity function, ultra deep surveys to go for the fainter galaxies, so smaller area but longer observations. We also have a choice of going blank fields or using gravitational lensing to aid us to magnify the view of distant galaxies. Borg survey that I've led falls into the blank field large area region of this discovery space. Just to show you some of the most recent results from Borg, we've been trying to push the discovery of the brightest galaxies at cosmic dawn to the highest redshift possible for Hubble. And here I'm showing you a couple of data points on the galaxy luminosity function at redshift 9, about 500 million years after the Big Bang, that we have been able to place with the latest set of Borg observations. And we find that galaxies brighter than the Milky Way were already in place at those early times, albeit very rare and challenging to find. Because of the expansion of the universe, Hubble only gives us rest frame UV information for these galaxies. But we have been able, while Spitzer was operational, to target the brightest galaxies that we discovered with the Hubble Borg survey with Spitzer IRAC observations. And so we've been able to get a glimpse of the rest frame optical emission from these sources. The Spitzer observations also helped us substantially to improve the photometric redshift estimates and the confidence that these bright objects that we see are with a high degree of certainty sources during the first billion years. If we move to the other end of the distribution of galaxy luminosities, observations with Hubble, aided by gravitational lensing, have characterized the luminosity function well for the much more common dwarf-like galaxies that are abundant. And because of the steep faint end slope of the galaxy luminosity function, they are expected to be the major contributors to the ionizing photon budget. And here we can see how with frontier fields Hubble observations, colleagues have been able to go down and observe galaxies that are as faint as AB magnitudes of minus 14. So with these few results, I hope to have convinced you that Hubble has enabled detailed measurements of the luminosity function. So essentially, with Hubble, we can count sources during the epoch of reionization fairly well, but those sources are still fuzzy red blobs. So leaving many open questions. If we push the discovery to higher and higher redshift, does the luminosity function remain still a Schechter-like as at lower redshift, or do we see evidence of evolution to different shapes, for example, double power laws? how efficient is star formation in the relatively high mass rare halos at those early cosmic times, which is linked again to the idea of what is the luminosity function at the brightest end. And do these sources have very young or relatively old stellar populations? And I say relatively old because let's not forget that the universe at those times was only 500–600 million years old. What is the environment where these galaxies that we observe are living? How many metals are there? Has dust already formed, or are these galaxies dust free? And partially, while we wait for the next generation facilities, we can address these questions by combining observations with theoretical modeling. And with several bright PhD students and early career researchers, I've been developing in parallel to the Hubble observations that we carried out to discover those galaxies, basic yet effective and insightful models to connect the evolution of the galaxy luminosity function to the assembly and growth of dark matter halos. And here in this figure, I'm showing a luminosity function model which we built by assuming that each dark matter halo is populated by one galaxy with a relationship between star formation efficiency in the dark matter halo, which depends on the halo mass, but not on the redshift. So we can calibrate the relation at one redshift, and then we have essentially a parameter-free model to describe the evolution of the galaxy luminosity function relative to the redshift at which we calibrated. And we can see here how successfully the model can reproduce the current observations from redshift 4 in yellow to redshift 10 in red, and also make predictions for what we expect at yet higher redshifts. With this type of basic modeling, we can also address a puzzling observational result on the lack of strong overdensities around the brightest galaxies and quasars that we see in the epoch of reionization. If we assume that the model is so simple that there is a one-to-one relationship between halo mass and galaxy luminosity, one would infer that the brightest galaxies are always hosted by the rarest, most massive dark matter halos, and so they should be surrounded by many siblings. However, if one naturally accounts for some scatter in the luminosity versus halo mass relation, then we can have a situation where we can increase the scatter essentially as much as we like, and as long as we adjust the median relationship between luminosity and halo mass, we can get the same luminosity functions. And here I'm showing a case at redshift 6 for illustrative purposes. But the more scatter there is in the luminosity versus halo mass right panel, we can see that the lower the typical dark matter halo mass is for the brightest object, because in the presence of substantial scatter, the brightest object will be a rare outlier that is overluminous for its mass. So the scatter is quite interesting because it constrains star formation processes, can be linked to more complex models, or can be measured in cosmological hydrodynamical simulations. So by quantifying the environment of the brightest galaxies at cosmic dawn, we can get some innovative insight on constraints for star formation processes. recently, with a University of Melbourne PhD student, we also used the same dark light model to predict the redshift evolution of the quasar luminosity function into the epoch of reionization, with similar assumptions on how we populate dark matter halos with quasars. Again, the model describes well, after a calibration at one redshift, the redshift evolution of the quasar luminosity function, and makes, interestingly, predictions for how many quasars we expect at redshift 8 and above. And concurrently with Borg collaborators, in particular with Takahiro Morishita, we are starting to search for point-like sources in the super Borg datasets, the collection of all Borg observations to date at redshift 8, and we're starting to set some interesting limits on that. Further progress, of course, will be greatly accelerated by the James Webb Space Telescope, finally at its place in L2. It will be an amazing flagship for global astronomy, larger mirror compared to Hubble, and infrared optimized to give us a fantastic view of galaxies at cosmic dawn. On the one hand, JWST can be used naturally to extend to higher redshift the discovery of distant galaxies that we've been carrying out quite efficiently with Hubble in these last 10 years. Based on modeling predictions, we expect to be able to detect galaxies with JWST out to likely redshift 14 or 15, so about 300 million years after the Big Bang. And we can see this prediction seems to be quite robust, irrespective of the depth versus area covered in a fixed observing time. So that will only differentiate between finding fainter galaxies on a smaller area, or rarer galaxies if we survey a wider field of view. On the other hand, even more interestingly for me personally, will be the use of James Webb to take spectra of existing galaxies that we know of at around redshift 7 to 9. We have a Cycle 1 program approved with NIRSPEC, led by one of the Borg postdocs, Guido Roberts Borsani, to follow up our 5 best redshift 8 sources. And we'll go from the fuzzy blob that we have at the moment in the H-band with Hubble, a few photometry data points with Hubble and Spitzer on the left, to beautiful spectra at high signal to noise that will give us continuum and emission lines such as oxygen 2 and oxygen 3, which will allow us to understand more details on the stellar properties of these sources. For fainter and more typical galaxies, gravitational lensing will, of course, help us, and early science results will be offered by the ERS program through the Looking Glass, led by my Borg collaborator, Tommaso Treu at UCLA. And we'll combine in particular in the Glass ERS program, the gravitational lensing observing Abel 2744 with JWST incredible sensitivity to characterize galaxies with a set of diverse instruments on JWST, including the Canadian Space Agency NIRISS instrument. To complement these galaxy observations during the epoch of reionization, the state of the intergalactic medium also needs to be investigated. Traditionally, this has been done with quasars absorption spectroscopy. However, quasars becomes rarer and fainter as the redshift increases. So an alternative would be to use other bright sources, and even with just a handful of gamma ray bursts at redshift greater than 7, since GRBs for a brief period of time are a million times brighter than their host galaxies, we would have a unique opportunity to gain insight on the intergalactic medium during the epoch of reionization. If the transients are followed up, are identified as high redshift and followed up promptly with spectroscopic observations, while the GRBs are brighter or comparable to quasars, so AB magnitudes of 20 or so. To enable JWST or 30-meter class spectroscopy of GRB afterglows, we need, however, two preliminary steps. First, we need an efficient all-sky gamma X-ray monitor with accurate localization. Swift is at the moment one such facility, but it is aging. Second, we require rapid photometric redshift determinations, and if we're looking for GRBs at high redshift, we need infrared observations. And these need to be carried out very promptly in the first 10 minutes or so if we want to start the follow-up observations with JWST sufficiently early that we can get our nice absorption spectra. So these first two steps are potential blocking points. So how can we address this need? And technology is evolving rapidly, and very much like the first computers were bigger than this room and less powerful than your phones, nanosatellites' capabilities are growing. So in principle, tiny focused missions or constellation of nanosatellites can offer cost, schedule advantages, and also access to advanced technology at lower readiness level, as these projects can naturally take more risk than a flagship such as the James Webb Space Telescopes. So there is a growing number of CubeSats and nanosatellites being launched in recent years. CubeSats are standardized dimension satellites, so that ride sharing, so hitchhiking a ride into space is very convenient. They've been introduced just at the turn of the last century as educational platforms, but the rapidly evolving technology led to a growing number of research CubeSats used today. Research applications were pioneered just about 10 years ago. And here in this image, I'm showing a 3U CubeSat, so 10 by 10 by 30 centimeter, 3 cube units. The Colorado Student Space Weather Experiment, which was launched in 2012, and led to 17 peer-reviewed articles, including one in Science, primarily carrying a high-energy particle telescope to study solar weather. For astronomy, we have three main challenges that are creating a barrier to the use of CubeSats. First, an astronomy CubeSat generally needs excellent attitude determination and control to remain stable while it stares at targets. This is being enabled by progress in miniaturization of star trackers and reaction wheels. Second, traditional communication with nanosatellites and CubeSats has relied to UHF radios, limiting greatly the bandwidth available. But S and X-band modems are emerging technologies and allowing the downlink of images and large data sets. Finally, depending on wavelength, thermal management can also be a challenge that needs to be addressed. A groundbreaking results for astronomical imaging from a CubeSat has been achieved a few years ago by the MIT JPL Asteria CubeSat, launched in 2017. Asteria demonstrated sub-arc-second pointing stability and high precision photometry at optical wavelengths. In this plot, we can see the RMS pointing stability on the vertical axis versus launch mass of the satellite on the horizontal axis, with the characteristic performance as a blue line. The lower below the blue line, the better. And we can see that Asteria here performs and as well as the Space Telescope's 10 times its mass. So with this promising landscape and context of rapid innovation, in the last few years, I started going from user of space telescopes such as Hubble and Spitzer to the development of nanosatellite instrumentation. So I founded at the University of Melbourne, the Melbourne Space Laboratory, focusing in particular on 3 core areas that have the potential to enable long-term infrared astrophysics observations from nanosatellites: active thermal control, low power resilient computing, and low latency communications with the satellites. At the moment, we have 3 active projects: the NanoPenguin hosted payload, a technology demonstration payload, the Spirit CubeSat that I will describe in the next few minutes, and then a mission in development for infrared astronomy, the Skyhopper Space Telescope. And so as PI of Spirit, I feel a great privilege and responsibility for having been selected to lead the first ever mission of the recently established Australian Space Agency. So Spirit is a 12-kilo nanosatellite with substantial ambition for its class of weight, as reflected by the approximately $6 million Australian budget for design, construction, and launch. Spirit will be the first made in Australia satellite to host a foreign space agency payload, a gamma and X-ray instrument from the Italian Space Agency. The key goals of Spirit are detection of gravitational wave counterparts and GRBs, technology demonstration for thermal control and rapid communication, and to promote the growth of the Australian space industry. In terms of astrophysics science case, we inherit the science case from the Italian-European high-energy modular ensemble of satellites, HERMES in short, which is a project aiming at high-energy transient localization, long GRBs and gravitational wave counterparts, studies of the GRB inner engine through characterization of the microsecond fast variability of the light curve, and potentially to setting limits on the granular structure of space-time by studying photon arrival time versus energy. These science requirements are reflected and achieved with an innovative gamma X-ray detector with a 2-band soft hard detection in the 3 to 300 kiloelectron volt range. The detection is based on a silicon drift detector, directly detecting the soft photons, while the harder photons interact with the scintillator crystals behind the detector, and then the optical light is detected by the STD. The detector has an exquisite time resolution, better than 400 nanoseconds, and the sensitivity and collecting area that give overall a similar performance to the Fermi gamma burst monitor instrument, despite being a miniaturized detector. The innovation on the Spirit satellite is that we're going to actively cool the detector to improve its performance. A single HERMES detector has a wide field of view, hence the localization is via triangulation of the signal. It's a time delay analysis similar to the gravitational wave detection strategy or to the original detection of GRBs through the Vela satellite network. Spirit is designed to survive the harsh radiation environment of a polar orbit, and it will complement the 6 other nanosatellites that are part of the HERMES technology and scientific pathfinder constellation that will be launched concurrently with the Spirit satellite next year in equatorial orbit. By having an orthogonal orbital plane with Spirit compared to the Hermes constellation, we expect a substantial improvement on the localization of long GRBs. This is ongoing work of my PhD student, Matt Thomas, who modeled the expected performance of the Hermes plus Spirit constellation. And we can see that while Hermes alone would typically characterize GRB locations to hundreds of square degrees of uncertainty, we can improve by a factor 10, adding Spirit, and have a localization similar to the Fermi GBM instrument. A core technological innovation on Spirit is the thermal management integrated subsystem. It's a subsystem designed for cooling and controlling precisely the temperature of a payload with requirements typical for infrared remote sensing of either astronomical sources or high sensitivity Earth observations. So Themis is in principle capable of cooling to 80 Kelvin cold tip with a Stirling cryocooler and maintain better than 1 degree Kelvin thermal stability. At Melbourne, we are developing space-optimized control electronics and deployable radiators to dissipate the heat generated by the cryocooler. Spirit will be a tech demo for the full capabilities of Themis and will operate the Hermes detector at 240 Kelvin, focusing on precision temperature management to have a uniform background across observations. Spirit is currently completing phase C, final design and fabrication, and passed the critical design review last April, in less than 1 year since funding and project kickoff, which happened in July 2020. I think this is really a demonstration of the agility of a CubeSat project compared to traditional space missions. And we expect at this stage to complete all development on the ground by the end of the year and be in orbit by next year, and then starting the next phase of the constellation expansion to achieve the full science objectives of the Spirit Hermes program. To summarize, today I showed you how Hubble transformed our view of galaxies and possibly in quasars at cosmic dawn, characterizing well the galaxy luminosity functions and the redshift evolution, which is mostly understood also thanks to comparison to theoretical numerical modeling. However, the star formation processes are still loosely unconstrained, but fortunately, the future is bright with JWST now undergoing commissioning of the instruments and smaller space telescope siblings hopefully joining JW and other major facilities. So thank you very much for your attention. Very happy to take any questions.
Thank you very much, Michele. That was very exciting. Thank you for sharing that with us. So as always, if you want to ask a question, simply raise your hand using the Zoom, or put it in the chat if you prefer for me to ask your question. Bob, go ahead.
Thank you for a really interesting talk. We had a colloquium last week where we learned that the plan with Starship is to get things into near Earth orbit at a level of like $5 a kilogram eventually. So I guess I'm wondering, if that future is realized, if we aren't on the cusp of something where we need not think of little CubeSats in space, but one could envision, rather than having space agencies put 1 or 2 meter telescopes in space, university departments could do it, or a consortia of universities could do it. So I'm wondering what you see for the future. Do you think that this trend towards miniaturization is going to define the future, or do you think it's going to look different?
I think, yeah, but you raise a really excellent point. The cost to access space is going down dramatically. However, we have not to forget that at the moment, the launch cost is not the limiting factor for the budget of a space program. Even for a CubeSat such as Spirit, launch represents less than 10% of the cost already. So even if we go down another factor 10, there is not a substantial difference. The cost at the moment is primarily with engineering, non-recurrent engineering, unique design for a single telescope. So I think where the most promising opportunity for cost saving comes from is if you can have a constellation of distributed aperture telescopes operating together. It does not necessarily need to be CubeSats, and here I fully agree with you. I actually feel that for full science exploitation, probably a microsatellite, maybe 100 kilos might be the sweet spot as the community matures. Universities maybe are more keen to take on a bit more risk with space-based investments, and indeed we can have a very, very fruitful collaboration. And the gamma X-ray community, I think, is coming together. There are many other nanosatellites for gamma X-ray detections that are being developed. For example, Burst Cube at NASA Goddard will also fly more or less concurrently with the Spirit Hermes constellation. So it's natural at those wavelengths to combine data together. If we're really ambitious, I could see, and that would be my long-term dream, instead of a JWST with a segmented mirror, we put on 1,000 of telescopes that are relatively small, but we combine them interferometrically in space, and therefore we can afford to leverage all the engineering effort done to develop like 1 unit of our distributed aperture, and then we clone it. We save a lot on testing, development costs and such.
Thank you.
Aaron has a question.
Hi, thanks for this really fantastic talk. Yeah, I had a question. Well, I had 2 questions, but one corresponds to something you just said. You know, it's very lovely to have more GRB nanosats up, but that's not a replacement for effective area. You know, you're still basically, you're gonna increase your field of regard and your coverage of the bright bursts, but you know, I think I don't know. I guess the question is, why do you think it's a better approach to do that than to push, which everyone else in the astronomical community at other wavelengths do, towards higher sensitivity?
I guess it's a good point, and it's a fair criticism that if we're on a small sat, the collecting area is ultimately the limiting factor. I see both approaches as equally valuable. I would not argue to have all small sats missions and not the flagships. But what I think is useful is to have the right mix of large facilities and small satellites. Strategically and pragmatically, in my situation in Australia, the Australian Space Agency was created just over 3 years ago. It has a tiny budget compared to more established and forward-thinking, ambitious space agencies, such as the Canadian Space Agency, are participating to major flagship projects. So essentially, my only mode of engagement to grow the space instrumentation community in Australia is to start from nanosatellites. But absolutely, the long-term vision is to build the community and make it ready to tackle more ambitious and complex projects.
Yeah, thank you. It wasn't, I maybe my comment wasn't really fair. It reflected a frustration with the fact that everyone thinks that you can do GRBs with a bunch of nanosats, and that's why there's no GRB probe or flagship in the decadal survey, or gamma ray in general. Anyway.
It's the top of the hour, so let me just take the opportunity now to just very warmly thank you, Michele, for this talk. And of course, we'll be sticking around for longer for those who want to stay, if you want to ask him more questions or to hear more about his research. But thank you very much, Michele.
Yeah. Thank you, Adam, and thank you all for the great discussion today.
So I guess I have a quick question for you. What fraction of bursts, you had these estimates for the localization, but presumably that's for the bright end of the luminosity function.
So as I was saying, the performance of a single Hermes instrument is not that far from the Fermi GBM. So to first approximation, that's what you're getting. Let me see. I don't have it. Let me share a paper. That's advantage of being on Zoom. That's from Fiore et al. 2021 with essentially the science case of the Hermes constellation. And this shows the GRBs detectable with the Hermes pathfinder in the E-peak versus flux plane. And essentially, the distribution of Fermi sources is in dashed red, and the GRBs detected by Hermes are pretty much in the same region. Of course, we're missing the faintest one, as you said. But the situation, I feel, is not too bad for what we have at the moment. Talking to Fabrizio, the PI of the Hermes project, I completely agree with you. We see the next phases of the constellation ideally to grow and go from a CubeSat to maybe a microsatellite that can host a larger detector. Here, there might be strategically some opportunities to collaborate with, communication constellations, Starlink and such. Maybe they could host payloads that look up.
I think actually, I know Jochen Greiner in Germany told me a few years ago that he was talking to people about putting gamma ray scintillators on the top of the Galileo GPS satellites.
I had a similar conversation with Jochen. I did not present today about the Skyhopper infrared space telescope, which was how my interest started on GRBs. nanosatellites to rapidly follow up essentially GRB's ground in space. And that originated with a conversation with Jochen, and Jochen is one of my collaborators on Skyhope.
Well, thanks for your great talk. I have to run, and I'll let other people ask questions, but we're signed up to speak tomorrow, so I look forward to
looking forward to continuing the discussion. Bye, Aaron.
Thanks. Do you have any questions, Stefan?
Yeah, I was wondering, do you have anything to say interesting about UV or ultraviolet proposals using small satellites?
Oh, yeah. So give me one moment. So the department is doing renovations while there is this semi-lockdown. So
we hear them.
Yeah, apologies. So ultraviolet is another super interesting area for nanosatellites, right? Because even a small satellite above the atmosphere can be very competitive. And there are a few nanosats ongoing. One very interesting is the CUTE, Colorado Ultraviolet Transit Explorer by Kevin France.
How are they doing? It's already, CUTE is already flying. Do you know how are they doing?
How
are they doing? I mean, they launched several months ago.
I was okay. I missed the CUTE launch. Yeah. Right. On the 27th of September.
Yes.
Yeah. Yeah. Look, I have not seen anything, and I missed the launch. I was on parental leave at the end of last year. I'm Googling it now. They seem excited that they launched, but they
nothing
are not
since
showing
October. Nothing since October.
And they don't even have to go all the way to L2.
Yeah.
Yeah.
So I might thanks for the tip. I might send Kevin an email to ask him how is CUTE doing.
There's been no report. That doesn't sound too good.
Yeah.
Stefan, are you involved in LOVES? Was it kind of a leading question?
Oh yes, I've been involved with LOVES from pretty early on. We also have another one in Poland that we're doing. In fact, we're making another submission in a few days. This one would be one that has two photometric telescopes. It would have of about of the 10 centimeter sort of range. One would be in the visible, one would be near ultraviolet. So the idea is to do simultaneous precise photometry of stellar oscillations and the like variable objects over about a 10-degree field of view.
Mm-hmm.
So it would be like a super bright, but just one satellite looking at this point. We're also looking spectroscopic options too.
And then I think Bradchenko has a wide field ultraviolet transit is a transient mission concept.
Well, of course, there's Ultrasat. Which is a very ambitious project. But the one you're referring to is who is it? Who is it?
Bradchenko.
Yes, I know the one. I think that's the. We talked about that here. It's changed names. I don't think they got funded most recently, but it's changed names a couple of times. I think it's called DADDAA at one point.
Yeah,
is that the one? And I think it had another name too. It might have a different name now.
No, I think the name is slightly different.
Yes, I think that yes. Just a minute. No, let's go back here. Where are we? Dorado. Here we are. Gucci. It also is called Gucci.
Yeah,
but
Gucci.
I think Dorado is Dorado. I think is the more recent name.
Which I think Gucci has been repackaged as a small explorer, right? So again, moving away from the CubeSat and.
I see.
I think it was funded at least for Phase B in the Explorer call a couple of years ago.
Right. I think they missed out in the most recent call decisions, because the ones that got, let me see, here it is. Here's the report. They selected Escape and COSI, the Compton spectrometer imager. That's COSI. They selected Escape, and they selected a gravitational UV. Oh, good. What year is that? I'm not sure. I didn't. I don't think they actually got. Oh, that was an old one. That was 2 years ago. So I don't think they got the latest one. They didn't get past the latest one. But anyway, I'm not sure. That's an old report.
So it strikes me, Michele, like you showed that picture of the lab you have there in Melbourne. How did you So you're not a trained instrumentalist, if I understand correctly.
I'm not trained as an instrumentalist, and I try to stay as much away from the lab as possible. I let the engineers do their work. I do mostly essentially project management, trying to get, my job I see is to get funding for the lab. I was very, very fortunate because I essentially ended up recruiting an extremely experienced thermal aerospace and mechanical aerospace engineer who had worked at Airbus Defence and Space in the UK for over 17 years. He was the thermal group lead, so he did the design of the thermal management for LISA Pathfinder, Solar Orbiter, Rosetta. So another dozen of ESA projects. But he's Australian, and essentially he was interested in coming back to Australia. He worked for a few years for defense CubeSats, but he didn't like the defense world. And so when I had a little bit of funding to recruit for a Phase A study of Skyhopper, he was keen to join. And then he had this huge amount of industry connections. And so the space industry in Australia is small. So we got really good connections, and we were able to put together a very good proposal to the Australian Space Agency to focus on the essentially industry growth aspects of Spirit. And I'm very proud to say that in the 100 pages or so of the Spirit proposal to the Australian Space Agency, science and astrophysics is not mentioned once. I sold them the Hermes gamma X-ray detector, saying that it was a remote sensing X and gamma ray instrument with future applications such as X-ray spectroscopy of asteroids if you fly it around an asteroid for mineral prospecting. Because the space agency is really keen on mining on the moon and on asteroids. So then after we were selected, I started telling the space agency, look, we really have a cool astrophysics mission, but it's unfortunate because the government created the space agency with the mandate to grow the Australian space industry. There is not a single mention of science. So that's an interesting challenge. But now we have a half a dozen engineers in the lab at the moment for Spirit. We are building two subsystems doing mission lead, project management, and then the local industry is building the platform. We're also hosting electric propulsion thrusters. So it's an interesting project, and it's a bit different from pure research or pure research management.
Yes,
and,
I noticed the website made several references to intellectual property.
yes.
IP development, I think. So,
but look, and we have been operating under these constraints. So it's not a traditional astrophysics space mission like the one that the Canadian Space Agency or NASA, another foreign space agency might fund. So we have to be navigating carefully the landscape. But so far it's been good. And our Italian colleagues have been fantastic to essentially provide all the research infrastructure for the project.
And they're building the detectors, if I remember correctly?
They're building the detector, the instrument. Yeah, it has been already built. It has been now tested, and we expect the Italian team to travel to Melbourne after Easter with the instrument for integration.
Neat. Huh.
Yeah.
That's so you get the kind of their experience too,
exactly
in the mix.
Yeah, exactly. So they will come down, and they will also help. Yeah, I've been, as I said, I've tried to recruit good engineers from overseas. The electronic design has been done by a postdoc who was for 5 years at Airbus in Spain and France, and he has worked on the ExoMars and the Curiosity rovers OBCs. So he has a lot of experience on electronic design for deep space. Yeah, so I have a really fun team to work with, and brilliant students as well. The University of Melbourne students about 5 years ago started out, they built their own 1U CubeSat from scratch. They only bought the radio commercially, which was very impressive. 1U, it has flown, they've been able to communicate with it. It has lasted for several months. And so they learned a lot of skills. And then I've been able to recruit a few of the best ones in the lab. One is a PhD student now. So it's good fun.
Are they all, the students working in the lab, are they like in your department, or do you have people from engineering? Or
I have it's about half and half. The co-PI is from engineering. So we have a bit more expertise on the engineering side as well, and the employees, essentially we split the funding, so half of the lab is employed by physics, half by engineering. Yeah,
neat.
Okay, well, I guess I'm going to have to sign off. So thank you very much.
Thanks, Stefan. It was great talking. Yeah, and hopefully we'll meet at some conference when the world returns to normal. And,
right.
If you ever are planning to come down to Australia, let me know. We generally, under normal circumstances, have funding to. If you're in Sydney, for example, we can fly you over to Melbourne. You can visit the lab, give a talk.
Well, thank you. Okay. Bye. Good night. Bye-bye.
And we can sign off now, and I'll see you in an hour and a half or so.
Yeah. And I think, let me see.
And you're speaking with Ajay in 10 minutes?
In 10 minutes, right?
Yeah. He's one of my students, so.
Okay.
Yeah, he's great. All right.
I see. I have AJ, Chris, then a break, and then I'll speak with you. And then there is an evening tea. What is just